in module 2, part E. Yeah, so here, let me complete that part first. Yeah, because this part, later you will see, yeah, and I will give you homework assignment number 1. In the homework assignment number 1, there are many questions related to this E.3. Yeah, so it's very important. Okay, so I like to first explain these these examples. Yeah, show that n to the d. Yeah, this one we call a power function. Yeah, this is a power function. Yeah, why we call it a power function? N is a variable. D is not variable. D is a constant. Okay, and this D constant, we just require here D greater or equal to 1. Yeah. Yeah. Actually, yeah. You know, any constant number greater or equal to 1. Yeah. Okay. Yeah. And the question asks you, the power function belongs to little o of that exponential function, a to the n. And this little o, it means the limit is 0. Okay? The power function n to the d over a to the n, this limit equals 0. That's the meaning of this little o. Okay? Yeah. So here you need to prove this limit equals 0. Okay? Yeah. All right. To prove that, yeah. So here we assume an integer, yeah. But later, because we here, yeah. So you know, here we assume the integer. That's for simplicity. Yeah. Because later, even if it's not integer, it is still correct. Okay? Yeah. It's not necessary an integer. Yeah. The reason in this example, to make our computation as easy as possible, we assume it's an integer. Okay? All right. Now, we calculate this limit by the L'Hopital's rule. And you can see I change from n to x. Yeah. The original question we used m integers, right? Positive integers. Yeah. But here I change to x. Remember, we switch to continuous variable. When we use positive integers, that's discrete variables. For discrete variables, we cannot take derivatives. Okay? Yeah, no definition of derivatives for discrete variables. So for that reason, I switch to continuous variable first. And before we apply L'Hopital's rule, we can see it is infinity over infinity indeterminate form, right? Infinity over infinity indeterminate form. Yeah, because the numerator goes to infinity and denominator also goes to infinity. Then after that, we can apply L'Hopital's rule, and you can see the numerator, we use the derivative of power function. This is the formula, derivative formula of a power function, d times x to the d minus 1 power. Yeah, that's a formula. Yeah, so you can find it, okay, easily. Yeah. Denominator also derivative of the exponential function. You can also find this formula. Okay. Natural log of A, that's the constant part, multiply original power function, not power, exponential function, a to the x. Okay. After that, you can see it is still in infinity over infinity indeterminate form, right? Yeah. So you can apply L'Hopital's rule another time. Yeah. This time, taking derivatives, numerator, denominator, it becomes a little harder. Yeah. But you can still do that. Okay. All right. You can keep doing this if you have infinity over infinity indeterminate form. Okay, so you can apply L'Hopital's rule many, many times until you reach some point. It is not an infinity over infinity indeterminate form. Yeah, like this one, because x to the d minus d, yeah, after you do d times, we assume d is an integer, d times, then x to the 0, that's 1. Then the numerator is not an indeterminate form. The numerator is d factorial. It's a fixed number. When x changes, the numerator does not change. So it is a fixed number. Then you cannot apply L'Hopital's rule another time. That's illegal. Okay? Because it's not infinity over infinity. It's not indeterminate form. The numerator is determinate. Yeah, it's determined. Sorry, not determined. It's determined. Okay? Determinate. Yeah. So that means you have to stop applying L'Hopital's rule, but you can get the answer directly because the numerator is a fixed number, denominator goes to infinity. Denominator still goes to infinity. Then you can see a fixed number over infinity, that's 0. Yeah. So the answer is, yeah, after simplification, yeah, because you get that. So it's 0. Yeah. Then we proved that little o notation. Yeah. We can go back to, after we prove it for the continuous variable, then we switch back to the discrete variable based on the definition of limit. Yeah. So I mentioned that before. Limit, when x goes to infinity, that means you can take any approximation way to the infinity, right? Yeah. Any approximation way to the infinity, it's legal. Now we take consecutive positive integer way, that's also legal, right? Yeah. So we go back to our original form. We take n consecutive positive integers. Yeah. So that's legal. Yeah. So we get a conclusion. Yeah. All right. Okay. Yeah, here. Yeah. Yeah. And in this question, so now after we prove it, then later we will use this. We will use this question. Okay. Yeah. So here, let me, yeah, because I mentioned homework assignment number 1, I will give you soon. Yeah. So we will use it. Okay. Yeah. When we use it, yeah, here we assume n to the d belongs to little o of a to the n, but when we use it, that d could be any positive d, is fine. Even non-integer is fine, okay? Yeah. But in my question, homework questions, I give you positive numbers, okay? Yeah. For simplicity, yeah. All right. And d could be very large, right? It's a constant number. Can we make the constant number fixed? Very large, right? All right. Then let's look at the A. A, we only require greater than 1, right? We only require it is greater than 1. Other than that, no other requirement. Okay? All right. So based on this result, then I make my homework questions. Many students got confused or they couldn't get to the point. Yeah. So because I ask you compare which one is larger when n is very big. Yeah. One is n to the, I use, 1 million. Okay. 1 million, 60 after 1. All right. Another one, a to the nth, I use 1 point, yeah, because a, we only need, it is greater than 1. Can I put many 1.01 to the nth? Right? So I ask you compare which is larger when n approaches infinity. Okay? Yep. If you answer this question by intuition, that could be wrong, right? Yeah. Because by intuition, most of you may feel, this number very close to 1. So then they just replace this number by 1. 1 to the nth, that's 1, or close to 1. How can you compare with this big expression, right? Yeah. But can you take a look at this result? We just prove it. That is correct. Mathematically, we proved it rigorously, right? It must be correct. Yeah. But that's different from the intuition of most of the students. That's something you will see in our homework assignment questions. Yeah. So here I emphasize this, big point. Yeah. All right. So let me complete remaining questions. Yeah. This time we compare log function and the power function. Can we treat this square root of n a power function? Because n to the 1/2. 1/2, although it's not an integer, it's positive, right? It's a positive, yeah. So we can treat it as n to the d with d greater than 0. So it is still a power function. But this time, we consider d a small number. Yeah, because we need to compare with log. We know when d is a large number, log function cannot compete with the power function. But how about when d is a small number? can log function compete with power function with D, a small positive number? Yeah. Here, we answer that question. Okay, we still apply L'Hopital's rule. So we switch to continuous variable X. Yeah. And we take derivatives because we know it's an infinity over infinity indeterminate form. Yeah. So it's legal to apply L'Hopital's rule. After the derivative, the numerator reciprocal, yeah, but you need to multiply that natural log of 2. Yeah. Denominator, the power function derivative formula, we know d times x to the d minus 1. Okay, yeah. So here, this formula we take, just from there, but d with d equals 1/2. Okay, we take that formula. D times x to the d minus 1 power. Yeah. All right, we need to do simplification after that. Yeah. After simplification, we get this expression, but this fraction, it's not an indeterminate form. So do not apply L'Hopital's rule another time. The numerator is a fixed number. It's 2, fixed number. So denominator goes to infinity. So a fixed number over infinity, it's 0. If it is 0, then we go back to the original function with discrete variable n, positive numbers, integers, yeah, positive integers. So we get that little o expression, yeah, little o expression. Yeah. Then our conclusion. Now here I use square root of n, square root of n. Yeah, that's just a special case, right? Root of n. And we can have some general case, right? Yeah, yeah. Here, example, this one, this time we consider general case. Yeah. So this time, log part, we use natural log. We use natural log because the log base is not that important. Log base 2, log base 10, log base any integer number here, not much difference comparing with we use natural log. Natural log is most convenient when we take derivative. Yeah, natural log. All right. Yeah. So ln of n, natural log belongs to little of n to the d. This time, I only need a d greater than 0. That's good enough. Yeah. So you can imagine d could be a very small positive number. Yeah. Not an integer here. Yeah. Because when we compare with log function, we do not need a large power function. Yeah. We mainly we consider small power function. Okay. All right. L'Hopital's rule again. Still, we use the continuous variable version of the limit. Then L'Hopital's rule, it's infinity over infinity. Yeah. So I always check it. Okay. Infinity over infinity. Then you take a derivative. Natural log, its derivative is the simplest, just reciprocal function, 1 over x. Then denominator the power function. Yeah. So the standard derivative formula for the power function. After simplification, we get this expression. It's not an indeterminate form. The numerator is a fixed number. It's 1. Denominator goes to infinity when x approaches infinity. So the answer, it's 0. Yeah. Here you can see we only need d is a positive number. This limit goes to infinity. No matter how small is that d. Okay? Yeah. So then, all right, then now I have 10 minutes before I finish our class today. So let me talk about another case that's quite confusing. Yeah. Another possible question I may give you in our homework assignment number 1. Now, similar to this one, I already explained this case. Okay, compare a power function and an exponential function. The exponential, the base is very close to 1, 1.00, many 0 after the decimal point, then 1. Compare that. Another similar question, yeah, based on this example. Yeah, it comes from this example. Okay, all right. Yeah, and that d, remember that positive d, that could be a very small number, but it's positive. It is close to 0, but it's not 0. Okay, then compare log base. Yeah, here I just use natural log. Yeah, okay, any base positive, base greater than 1. Yeah, but we require base greater than 1. Okay, yeah, natural log of n, and then power function n to the d. Can I choose a very small d? But it's positive. Okay, so here I choose 0.000. I put many zeros. 1. Okay, this power function expression. I'll ask you compare these two functions when n, approaches to infinity. Okay, yeah, so very, very large. Yeah, which one eventually is larger? Yeah, eventually is larger. Okay, yeah. If you answer this question by intuition, you may feel n to the 0 point, many 0, 1, the exponent number is very close to 0, right? Then you may feel n to the 0, that's close to 1, right? We know n to the 0, it is 1. Yeah. Some student answer the question by intuition, okay, then it's very likely they compare this function with this result. Yeah. Exponent number so close to 0, then it's very likely they replace the exponent number by 0, then this power function is, they feel close to 1. How can you use 1 to compete with natural log? We know natural log goes to infinity, right? But your power function, they feel close to 1. How can you compete with natural log, right? Yeah. But can you take a look at our example 2.7? In 2.7 tells us the log function cannot compete with the power function n to the d if d is positive. We don't mind how small is the d number, how close is the d number to 0. We don't care, but eventually n to the d, that power function will outgrow the log function. Okay? Yeah. Although that it could take very long, a very big n number, but we allow n approaches to infinity, right? So we don't care how large is that n. When n approaches 0, eventually it will be there, right? Eventually n will pass that line. Okay? Yeah. Then some students, they argue with me in this way, yeah, because they try to apply calculators, you know, even some online. Yeah, we know our hand calculator, little app on our cell phone may not be very powerful, right? It's quite limited. Yeah, our hand calculator, you know, any version, any kind, so its computing capability is quite limited. Yeah, but for calculation, for this question, we may need a lot more computing power, right? Yeah. So some students, they can find some online computing, you know, more powerful calculator online. So they try to do some experiments. Then, so because when you do experiments, that n to the 0.00001, that function increases very slow, very flat. Okay, the curve is very, very flat, you know. Yeah, because the reason is this: your n cannot be too big, right? Your n cannot be too big when you do calculation. Okay, it grows very, very slow, and your calculator cannot tell you its behavior when n is extremely huge. The calculator has the limit. It cannot tell you, you know, its behavior when n is extremely big. Okay, so based on your experiments in some online calculator, you may not get the correct answer. Okay, yeah. So some students use the online computing result, you know, to argue with me which one is larger, because you can never use the sufficiently large n. Yeah, because the n you use relatively small. Yeah, but when we do math calculation, we can imagine super big n, right? N goes to infinity. Think about how big n is possible. Okay, yeah. And actually, I remember, in order to convince that student, I found that limit line, or that big n number, right? I found that expression. So I told that student, so that n equals, you know, for example, 10 to the, yeah, I found that n expression. Then I told them, if you use this big number, then the power function will beat the log function. Okay, yeah. So here, I use this chance. I give you the, possible results derived from these two examples, 2.5 and 2.7. Yeah, you will have two similar questions. One similar to the, first one, another from the second one. Okay, yeah, these two questions in our home assignment number 1. Okay, all right. So let me stop right here.